Thanks for watching my video today. Let's see our Euler-Mascheroni constant. Okay, so here is another integral representation of Euler-Mascheroni constant. Then is the integral from 0 to x 1 minus e to the negative t upon t dt minus integral from x to infinity e to the negative t upon t dt minus natural log of x is nothing but our Euler-Mascheroni constant. Okay, here x is greater than 0. Okay, let's start with this. Now we're going to prove left hand side. Okay, left hand side is equal to right hand side. So left hand side is the integral from 0 to x 1 minus e to the negative t upon t dt minus integral from x to infinity e to the negative t upon t dt minus log n. Okay, now integral from 0 to x 1 minus e to the negative t upon t dt. Now adding and subtracting these two. Okay, then is the integral from x to infinity dt upon t. Here also we are going to subtract again x to infinity dt upon t, and this is similarly and this one. Now left hand side is the integral from 0 to x 1 minus e to the negative t upon t dt, and see this two. Okay, this one plus integral from x to infinity okay, combining these two, okay, these two combining positive integral from x to infinity, same thing, right? 1 minus e to the negative t upon t, this one, right? And minus integral from x to infinity dt upon t minus log n. Okay, I hope that is clear. So if you see here, the integrand is the same, so, and the upper bound and lower bound of these two integral is from 0 to x to infinity, right? Then the same as 0 to infinity, right? So 0 to infinity 1 minus e to the negative t upon t dt minus integral from x to infinity dt upon t minus log n. Okay, now I'm going to break out again this one. Left hand side is equal to the integral from 0 to infinity dt upon t minus integral from 0 to infinity e to the negative t upon t dt minus integral from x to infinity dt upon t minus log n. Okay, now we're going to use the limit representation of e to the negative t. Then this left hand side is equal to integral from 0 to infinity dt upon t minus integral from 0 to infinity. This the limit representation of e to the negative t is nothing but limit n tends to infinity 1 minus t by n to the power n upon t dt. Okay, minus integral from x to infinity dt upon t minus log n. Now this limit taking out here, so limit n tends to infinity. Because of this, so all the infinity will be changed to n. Okay, the integral from 0 to n dt upon t minus integral from 0 to n 1 minus t by n to the power n upon t dt minus integral from x to n 1 over t dt minus log n. Okay, now next page, this is the, now we are going to combine these two again. Okay, so left hand side is nothing but the limit n tends to infinity, so now we are going to combine these two, and is 1 minus t by n to the power n upon t dt minus, so this one integration of 1 over t is nothing but log t, right? Then is from x to n, so it will be negative log n plus log x minus log x. Okay, now these two can get cancelled out. Now putting that t by n is equal to x, okay, then dt is n dx. Okay, therefore limit n tends to infinity, so integral from when t is 0, so x will be 0, right? So 0. When t is n, then x will be 1, right? N by n, this is 1. 1 minus x to the power n upon t is nothing but, if you find out here t, then it will be nx, right? Nx, so nx, and dt is nothing but n dx, so n and n will get cancelled again, right? Minus log n. So then this limit n tends to infinity, integral from 0 to 1 minus x to the n upon x dx minus log n. Now we are going to use, okay, let's substitute that 1 minus x is equal to u, so negative dx is du, or 1 minus u is just x. Okay, now limit n tends to infinity, integral from when n is 0, when x is 0, u will be 1, right? When x is 1, so u will be 0, so 1 minus x is nothing but u to the n upon x, finding out here x 1 minus u, right? And dx is negative du minus log n. Now because of this negative sign, so this or integral limit, okay, upper and lower limit will be interchanged, okay. So limit n tends to infinity, integral from 0 to 1 minus u to the n upon 1 minus u du minus log n. Okay, now let's see this one. So if you see this carefully, this one, this is nothing but geometric progression, GP, okay. So then is the sum from k equal to 0 to n minus 1, u to the k is nothing but 1 minus u to the n upon 1 minus u. This is GP, okay. You can see that sum of geometric progression, okay, in that. So then is limit n tends to infinity, this is sum, right? Sum from k equal to 0 to n minus 1, integral from 0 to 1 u to the k du minus log n. Here changing this integral sign and summation sign, okay. Limit n tends to infinity, sum from k equal to 0 to n minus 1. Now if you solve this one, so it will be u to the k plus 1 upon k plus 1 from 0 to 1. When it is 1, it will be 1 over k plus 1, this one. When it is 0, so this whole term will be 0, right? Minus log n, which is limit n tends to infinity, sum from k equal to 1 to, here it is start from 0, right? So if you expand this sum from k equal to 0 to n minus 1 over k plus 1. So if you expand this, it will start from 1 plus 1 by 2 plus 1 by 3 plus and so on plus 1 over n, right? So therefore, instead of writing this one, so I'm going to change it, k equal to 1 to n 1 over k minus log n. This is nothing but the Euler-Mascheroni constant, okay. Hence proof. Therefore original integral, this one is on the left hand side, right? So we solve the left hand side, so we solve here, so we get our Euler-Mascheroni constant, this one. Therefore the integral from 0 to x 1 minus e to the negative t upon t dt is minus integral from x to infinity e to the negative t upon t dt minus natural log of x is nothing but our Euler-Mascheroni constant. So this is another integral representation of the Euler-Mascheroni constant, okay. Hence proof.